Alrighty, here's another example of finding the Thevenin equivalent of this circuit. Again, we have two values that we need to find. We need to determine the open circuit voltage, which is the voltage across there with no load connected. And then we also need to determine the Thevenin equivalent resistance, which in this one we'll do a couple of different ways. Alrighty, first of all, V open circuit. That's the voltage at this node, noting that the current leaving this node going in that direction, call it I, is equal to 0. So let's call this node here V sub A. We've got V open circuit there, and let's write the node equations at these two nodes. Noting first of all, before we get ahead of ourselves, that this dependent current source is pushing current into the node going in this direction with an amount of 1.2 times I0, where I0 is the current flowing through the 3 ohm resistor. So before we get started, let's just note that I0 is equal to 15 minus V sub A divided by 3. We're going to need that here in just a second. Alrighty, summing the currents leaving V sub A. Going in that direction, we have V sub A minus 15 divided by 3. Plus the current coming down through the 6 ohm resistor is going to be V sub A divided by 6. The current leaving V sub A, or the A node going through the 4 ohm resistor, is going to be V sub A, the voltage on this side, minus the voltage on that side, which is VOC, the open circuit voltage, divided by 4. Now we have coming into the node, it's going to be minus 1.2 times I0, but I0 we have already expressed as 15 minus V sub A divided by 3. So there's 1, 2, 3, 4 branches, 1, 2, 3, 4 terms. The sum of those 4 things needs to equal 0. Writing the node equation at the other node there, which we're calling VOC, we have two non-zero currents. We've got the current leaving this node going through the 4 ohm resistor in this direction is VOC minus V sub A divided by 4, plus the current leaving this node going in that way, which is 1.2 times I0, so plus 1.2 times I0, which we've already expressed as 15 minus V sub A divided by 3. As noted, or as we've already noted, the current leaving going in this direction is 0, so the sum of those two currents must equal 0. I'm going to skip the grimy algebra, but after you've simplified this down, you come up with V sub A times 1.15 plus VOC times a negative 0.25 equals 11. The top equation simplifies to that, and the bottom equation, the second equation, simplifies to V sub A times a negative 0.65 plus VOC times 0.25 equals negative 6. And when you plug that into your matrix solver, or however you do it, you get then that V sub A equals 10 volts, and VOC, which is our Thevenin voltage, equals 2 volts. Now, we have three different methods of finding the Thevenin resistance. The first method would be to short out the terminals A, B and determine the short circuit current, and then R Thevenin equals V open circuit divided by I short circuit. We're going to do that here in just a minute. The second method only works when you have independent sources only, or when you only have independent sources. The fact that we have this dependent source here makes it so that method 2 doesn't work. Method 3 is also going to work. We'll do that here in just a second. Method 3 involves shorting out this voltage source, deactivating the voltage source, and then applying a test voltage. So let's start with the short circuit method. Let's short this out, call that I short circuit, and now determine the current in that short circuit. We need to note a couple of things. First of all, as we short this out, we now know that the voltage there equals 0. So we only have one node where we have an unknown voltage. We're going to calculate V sub A, and once we know V sub A, we'll then write a node equation at this node, noting that V0 equals 0, but the equation will then be in terms of I short circuit. We'll be able to calculate I short circuit. Let's go ahead and do it. It's probably easier than it is. It's probably easier to show it than it is to talk about it. So let's just work on over here. Writing the node equation at the A node, we have V sub A minus 15 divided by 3 plus V sub A divided by 6 plus V sub A divided by 4 minus 1.2 times. Now notice that I0, even though we've shorted this out, I0 is still 15 minus V sub A divided by 3. So it'll be minus 1.2 times 15 minus V sub A divided by 3, and the sum of those terms has to equal 0. Now when you go through and simplify that and solve for V sub A, you get that V sub A is equal to 9.565 volts. Now that we know V sub A with this output short-circuited, we can go ahead and write a node equation at this node. We'll do it in terms of V sub A, but V sub A is going to equal 9.565. Let's just do it and show you what we get here. So we're going to have the current leaving this node going in that direction is going to be 0. Oops. No. Yeah, 0. The voltage there is 0. 0 minus V sub A, which is 9.565, divided by 4, plus the current going in this direction, which is 1.2 times I0. I0 is 15 minus V sub A, so that's going to be 15 minus 9.565 divided by 3. Then we have I short circuit leaving, so that would be plus I short circuit equals 0, or let's just bring the short circuit over to the other side as a equals minus I short circuit. Running out of room here. Alright, let's continue on now and solve for I short circuit, and when you do that, you get that I short circuit is equal to 0.2173 amps. We now know V open circuit is 2, I short circuit is that, R Thevenin is equal to the ratio of V open circuit to I short circuit, which equals 2 divided by 0.2173, and that equals 9.2 ohms. And we can now draw our Thevenin equivalent circuit. It consists of a 2-volt source with a 9.2 ohm resistor in series, and there are our A and B terminals. Thus, this nice, concise little circuit, if all we're interested in is the terminal characteristics, this models this more complex circuit. Now let's just show that we get the same R Thevenin using method 3. Method 3 requires us to deactivate the independent sources. So this is a voltage source, we turn it to 0 volts. That is effectively shorting it out. And we then apply a test voltage, call it V test, which then drives a current I test into the circuit. We have two nodes. We've got the node here, the node here. We'll call this one again V sub A, noting that this V sub A is different than the V sub A that we did before. The V sub A that we did before had a 15-volt source connected at this point. This circuit has that 15-volt source shorted out. So we're going to use the same name, V sub A, and over here this is no longer 0. This is now V test. Let's go ahead and write the node equation for this A node. So the current leaving, noting also we're going to need this. I0 in this case is the current going in that direction. That's going to equal 0 minus V sub A divided by 3, or just negative V sub A over 3. Alrighty, now let's write the node equation there. The current leaving this node going in this direction is going to be V sub A minus 0, because that's now shorted out, divided by 3, plus V sub A divided by 6, plus V sub A minus, we're now talking about the current leaving this node going in through the 4 ohm resistor. It's going to be V sub A minus V test over 4 minus the current entering this node from the dependent source. That's going to be minus, because it's entering, 1.2 times I0, and I0 is negative V sub A over 3. 1, 2, 3, 4 terms. The sum of those 4 terms must equal 0. Now, let's write the node equation over here at the test node. We have 3 branches, 3 currents. The current leaving the node going in this direction is going to be V test minus V sub A divided by 4 plus, now this current here is leaving the node, so it'll be plus 1.2 I0, but I0 we've determined to be negative V sub A over 3, negative V sub A over 3. Now IT is coming in, so that would be minus I test. Let's just take it to the other side as a positive I test and say then that those 2 terms will equal positive I test. Now you'll notice that we have 3 unknowns, V sub A, V test, and I test, but we have only 2 equations. But that's alright, because what we're going to try and do is, through algebraic manipulation, come up with an expression here in this upper equation that gives us V sub A in terms of V test. We'll then plug in down here in the second equation for V sub A. All of the terms then will have V test, will either have factors of V test or I test. We'll factor out the V test and be able to make the ratio of V test over I test. And again, that's what our Thevenin is the ratio of V test over I test. So this upper equation cleans up to give us 1.15 V sub A is equal to 0.25 VT. So V sub A then is equal to 0.2174 V test. Let's take those values in then and plug them in down here. In fact, let's just clean this one up a little bit down here. Let's rewrite this bottom one as we're going to have V test times 1/4. That's the only V test term. And then we're going to have plus V sub A times, we've got a negative 1/4, and we have a negative 1.2 over 3 equals I test. Now we'll take this expression for V sub A in terms of V test and plug it in down here for V sub A, and we have 1/4 V test plus V sub A is 0.2174 V test times a negative 1/4 minus 1.2 over 3, and that equals I test. Now you go through and clean this up, and we get 0.10869 V test equals I test. Now, forming the ratio of V test over I test gives us our Thevenin. So our Thevenin equals V test over I test, which equals 1 over 0.10869, which once again equals 9.2 ohms. Thus, we get the same R Thevenin from method 3 as we got from method 1 on the previous page. Method 2 doesn't work because there's the dependent source in there.